Guys, how's it going? So here we're going to start section 5.3. We're going to start to solve trigonometric equations. Okay, so you guys should have a lot of fun with this, mostly because everyone here tends to be very, very good at solving equations. Now the only thing is now these are dealing with some trigonometric functions instead. All right, so your first goal, obviously we're solving for the variable of x, right? But the first goal is always to isolate the trigonometric function, right? So if you look here, we already have the trigonometric function isolated, okay? We already have the sine of x is equal to the 1/2, okay? So what your mentality needs to kind of be is you need to figure out, okay, where is sine equal to the 1/2 on this interval? Okay, so basically the unit circle. We're going to look at, think of the unit circle and try to identify where is sine of x equal to 1/2, right? So there's actually two locations, okay? The first location is at the angle pi over 6. And then the second location is at the angle of 5 pi over 6, okay? Now, these two are the solutions on this particular interval. However, the problem never told us that to find the solution based on a closed interval. It actually just said find the solution, right? So what we have to think about is we have to think about sine being periodic, right? And sine is going to occur multiple times throughout the domain, right? Particular values. So if I look here really quickly, right? Notice, okay, that here's your sine function graph, okay? Here's the 1/2 value for y. How many times is it touching the sine function? It's touching it a whole bunch of times, right? So all of these are technically locations where sine is equal to 1/2. Now, since sine travels infinitely in both directions, there's going to be an infinite number of solutions, but we actually can figure out these solutions. What I want you to notice here, okay, is that this one here is pi over 6, but this one is pi over 6 plus 2 pi. Now, why do you think it's a difference of 2 pi? Well, it's because the period of sine is 2 pi. Also, because to find the coterminal, we also add 2 pi to the angle, right? Because we're finding the coterminal of the function. So because the period of the sine function is 2 pi, every 2 pi, another pi over 6 interval is going to occur. Same thing here with the 5 pi over 6. We have 5 pi over 6 plus 2 pi and 5 pi over 6. Okay, again, notice that they have the minus 2 pi's here. So every 2 pi, you're going to have another solution. So because this one specifically said that we are not going to have a closed interval, here it just said solve for sine, so we can't just say pi over 6 to 5 pi over 6. We actually have to say every single solution. So the actual answer here is going to be pi over 6, okay, plus 2 pi. We're going to go 2 pi k, where k belongs to z, okay, and here we're going to say 5 pi over 6 plus the 2 pi k, where k belongs to z. All right, so that's going to be the solutions for this equation. Again, because they did not restrict us on a domain, but we know based on the unit circle that between 0 and 2 pi, that these two are the solutions here. So, that's what we kind of wanted to go with. And here, look here, here's the unit circle, right? So here are the two locations. Again, to find every single angle that's at this terminal position, you would have to add 2 pi to get to that position, and same thing here, you would have to add 2 pi to get to that position. All right, so it's just a matter of identifying it in different ways. Here's a graph setting, here's the unit circle setting, and then an equation based. Okay, once we, hopefully by now we're starting to get accustomed to some of these values, so they should be easier to attain. All right, so let's look at our first equation here. All right, so here we want to solve, so just like any other equation, we want to get all of the trigonometric functions on one side and all the values to the other side, because this one kind of follows a linear model, right? So we're going to start with sine x plus radical 2 equals negative sine x. First thing we're going to do is add sine to both sides. So we're going to get 2 sine x is equal to, 2 sine x plus radical 2 is equal to 0. 2 sine x is going to be equal to negative radical 2. Sine x is equal to negative radical 2 over 2. Okay, so what we're looking for here is we're looking for where sine is going to be equal to negative radical 2 over 2. Okay, again, in the closed interval, we know that that's going to be at 5 pi over 4 and at 7 pi over 4. So those are the two locations where sine is going to be equal to negative radical 2. However, there is no restriction on the solution set. So this is going to be plus 2 pi k, where k belongs to z. And this is going to be plus 2 pi k, where k belongs to z. All right, so we want to include the entire solution set over the entire length of time on the function. All right, so there you go. That is the first example. Nice linear model, okay, nothing too crazy. Again, just knowing where the sine of x is equal to negative radical 2 over 2 is going to be important. Okay, let's look at our second example. Again, at any point in time, if you guys want to pause these so you can work on these on your own, you can. There's no issue there. All right, I actually prefer that because I feel like you guys will do a little bit better, you know, working with that. All right, so here's a tangent function. All right, so here's the first one that's not sine. So let's take a look at how we're going to solve this. So 3 tangent squared x is equal to 1. Then we're going to get tangent squared x is equal to 1 over 3. At this point, we're going to want to take the square root. So it's going to be tangent x is going to be equal to plus and minus radical 1/3. So when we simplify that, that's just going to give me plus or minus radical 3 over 3. Okay, so now you have to be careful because again, since you're taking the square root, you need to include the plus or minus. Do not forget about the plus or minus, all right? Now, what's the period of tangent? Okay, again, this is why all of this connects well because, you know, we had to graph first to understand the periods. The period's pi, okay? So if the period's pi, we're looking for all the solutions where tangent is equal to positive radical 3 and negative radical 3 in the interval of 0 to pi. Let me make that a bracket. Okay, so from 0 to pi, where is tangent equal to radical 3 over 3? Both positive and negative. Okay, so the first solution is at pi over 6, and the second solution is at 5 pi over 6. Now, what you have to be very careful of is, again, the original problem did not say just between the period, okay? It wants it throughout the entire length of the number line. So we're going to have to add the period, which is pi, times k, where k belongs to z. And then we're going to have to add the period here, plus k, where k belongs to z. Okay, so again, because the period of tangent is different than the periods of sines and cosines, you just have to make note of that. Just be careful with what function you're working with, understand the period. Their only real difference is tangent and cotangent are pi, whereas sine, cosine, secant, and cosecant are all 2 pi. All right, so just be aware of that when you're working with this, but again, it shouldn't be too much of an issue. Okay, so here are your 2 solutions for this one. Okay, again, pause the video if you want to try this one, okay? All right, now this one here, okay, it has 2 functions. First, it has cotangent and cosine. So we have to find a way to actually solve this. So what we're going to do here is we're going to move everything to one side because I do see something that we can do here with the cotan. If I move everything to one side here, notice that I can factor out what? I can factor out the cotangent. Good. So we're going to factor out the cotangent, and I'm going to be left with cosine squared x minus 2 equals 0. Okay. All right, so now we are going to go ahead and find a way to solve this. So we use the zero product property. Cotangent of x is equal to 0, and then the cosine squared of x minus 2 is equal to 0. All right, and then we're just going to, and then we're going to go ahead and solve these equations. All right, so now here, we have to identify where is cotangent equal to 0. Again, it's on the interval from 0 to pi, and that's only going to be at pi over 2. Okay, so there's only one solution for this one. Okay, now this one we need to solve. So cotangent squared x equals 2. Now we're going to take the square root, so cosine x is equal to plus or minus radical 2. All right, now we do have a problem with this second one here. Here's the reason why. Notice that we're saying what angle is going to give us a cosine of radical 2, but notice that this value is going to be greater than 1. Remember, the range for cosine is going to go from -1 to 1, so there's no way that this could be a solution to our problem, okay? So therefore, this one is going to be a no solution. Okay, so the only solution we have for this problem is this one. Okay, again, no restriction on the domain. So what would be the addition part of this? We would have to add pi k, where k belongs to z, because we are dealing with a cotangent period in the first equation. Okay, so again, so no solution from this. Okay, so if we have no solution for that, it's not part of the solution set. The only solution we're going to have here is the pi over 2. Okay, and every pi over 2 plus pi k. All right, so that's that one there. Okay, next one. Find all solutions of 2 sine squared x minus sine x minus 1 is equal to 0. Now this one here specifically is giving us an interval, so we don't have to find all of them, we just have to find the ones that are on this specific interval. Okay, all right, so notice that it's kind of quadratic form. Okay, so we can actually factor this the same way we would normally a quadratic. All right, so again, if you factor this, you'll get the same thing as the factors for this one here. All right, so when we factor this, I'm going to get 2 sine x plus 1 sine x minus 1 is equal to 0. All right, now what we're going to do here is we're going to go ahead and set each of these factors equal to 0. And we're going to solve each of these equations. So here we get 2 sine x equals -1, sine x equals -1/2. So x is going to be the two values where sine is equal to -1/2. So x is going to be 7 pi over 6, and x is going to be 11 pi over 6. Those are the two function values at which sine is going to be equal to -1/2. Here we're looking at the function value where sine is equal to 1, so that's going to be only at pi over 2. Okay, so now those are your three solutions. Again, because they gave us this closed interval here, we only have to provide the solutions that are between 0 and 2 pi. Okay, there's no need to provide the solutions for the entire number line. Okay, now here's one, okay, that's a little different. Okay, now if you notice, we have sine squared and cosine, so we can't just factor because they're not even the same function. Okay, so now this one is where knowing your identities will help you. Okay, so now I'll ask you the question, is there any way I can keep this so quadratic and convert one of these two into the other? Okay, if you said I can take sine squared and convert that into 1 minus cosine squared, you are correct. Now notice when I do this, here's the beauty about the identities. When I do this, okay, I now only have cosine squareds, but it's still a quadratic, so I could still factor it later on. All right, so let's go ahead and distribute this 2, so I get 2 minus 2 cosine squared x plus 3 cosine x minus 3 equals 0. All right, so let's combine like terms. I'm going to get -2 cosine squared x plus 3 cosine x minus 1 is equal to 0. And sometimes we don't really like how that looks, so what we can do is we can just rewrite that. Because of the leading coefficient being negative, we can rewrite that as 2 cosine squared x minus 3 cosine x plus 1 equals 0. Okay, and we'll get the same solutions. All right, so when we factor this, I get 2 cosine x minus 1 times cosine x minus 1. All right, so let's go ahead and solve this. So cosine x here is going to be equal to 1/2. Cosine x here is going to be equal to 1. So we're looking for all the solution sets. Again, no restrictive domain. So what's the domain of sine? Of cosine. Cosine's 2 pi. So we're going to have cosine x equals 1/2. X equals pi over 3 plus 2 pi k, where k belongs to z. We get 5 pi over 3 plus 2 pi k, where k belongs to z. And then we get 2 pi plus 2 pi k. Okay, or 0 plus 2 pi k. If we wanted to work with that, that's also another way to kind of write this. Okay, because cosine is equal to 1 at 0, and then you add 2 pi k because of the period. And this is where k belongs to z. All right, so again, using your unit circle is going to be very helpful for you guys. If you don't know the function values at this point, and again, identities will be very useful once we work with those. All right, but here you go. This is over the entire number line. That's kind of where you want to go with this one. All right, next one. Find all the solutions of cosine x plus 1 equals sine x in the interval 0 to 2 pi, okay? All right, so now this one, since we have both of the two different trig functions, it's going to be hard to work with this because none of them are squared. Now, that's a key indicator. Since none of them are squared, we can try to force them to be squared. So let's do cosine x plus 1 equals sine x. Let's see what happens when we square both sides. We can force them to be squares. We're going to get cosine squared x plus 2 cosine x plus 1 equals sine squared x. Okay, so now, does it make sense to convert sines into cosines or cosines into sines? I think it makes more sense to take this sine and convert it into a cosine squared. Okay, so we're going to go ahead and do that. Okay, and then we can convert, okay, or move everything over to one side. So if I subtract the ones are going to cancel. If I add cosine squared, I get 2 cosine squared x plus 2 cosine x equals 0. We factor 2 cosine x, and that's going to be cosine x plus 1 equals 0. All right, so cosine x is going to be 0 in the first equation, and cosine x is going to equal to -1 in the second equation. All right, so we're looking for where cosine is equal to 0 and cosine is equal to -1. Now, they only told us on this restricted domain of 0 to 2 pi, so we're only going to find the solutions of cosine, where cosine is equal to 0 from 0 to 2 pi, and where cosine is equal to -1 from 0 to 2 pi. All right, so cosine is 0 at pi over 2, 3 pi over 2, and then cosine is equal to -1 at pi. So these are your only 3 solutions in this problem, okay? Now, we do have a little bit of a problem. Here's what your problem is going to be. Anytime you square an equation, you're going to be adding solutions that are extraneous, that don't belong to the problem. And you learned about extraneous solutions when we worked in the past, okay? So what you need to figure out here is you need to figure out which one of these angles here, okay, are extraneous when you substitute them back into the original, okay? So let's take a look here. If I plug in pi over 2 into the equation, I get cosine of pi over 2. The cosine of pi over 2 is 0, okay? So I'm going to do the work up here, 0. Plus 1 is equal to the sine of pi over 2. What's the sine of pi over 2? The sine of pi over 2 is 1. Okay, so that checks out. Okay, so pi over 2 is definitely one of our solutions. Let's look at 3 pi over 2. The cosine of 3 pi over 2 is 0. The plus 1 and the sine of 3 pi over 2 is actually -1. Okay, now those do not equal, so we call this an extraneous solution. Okay, now the last one is pi. The cosine of pi is -1. Plus 1 is equal to the sine of pi, which is 0. So that one checks out. Okay, so in reality, we only have the solution of x equals pi over 2. This one's extraneous. Again, the only time we should really be looking for extraneous solutions is when we're squaring an equation. If we square an equation, that's going to give us extra solutions that we never really wanted, okay? And that's just a property that occurs when we work with equations. You've done that in the past when we worked with radicals. You're always adding some extra solutions that wouldn't normally be there. So these are the solutions that shouldn't be there because of the fact that we squared it, okay? So only pi over 2 and pi are the solutions for this one. Okay, now this one is different. And the reason why this one's different is because, look, we have here a 3t, okay? Now, this is what we call a multiple angle. We'll get into the identities that involve these multiple angles moving forward. But we need to kind of figure out here how to solve this. So what you're going to do is you're going to kind of do the same thing. All right, so think of it as, how do I say it? Think of this like as just another way of approaching the problem. So what we're going to do is I'm going to just say that u is equal to 3t. Okay, now we pick u, you could pick any variable, but u is typically the one we use for any time we do a substitution. Okay, so what I'm going to do is I'm just going to substitute the u into this problem. Okay, and then I'm going to solve for u. Okay, now the reason I do this is because now my problem looks normal. Okay, and I can solve this with no issue. So I get 2 cosine u equals 1 cosine u equals 1/2. Okay, now notice that this is very simple. Where is cosine equal to 1/2? Okay, that value is going to be at pi over 3. Okay, and what's the other location? The other location is 5 pi over 3. Now remember, we're not solving for u, we're actually solving for t. Now notice, because u is equal to t, I can just substitute this back into my problem, right? So what I need to know first is that u is equal to pi over 3 plus 2 pi k. And I need to know that u is equal to 5 pi over 3 plus 2 pi k. Okay? Now what I'm going to do is I'm actually going to substitute 3t for u. So 3t is equal to pi over 3 plus 2 pi k. 3t is equal to 5 pi over 3 plus 2 pi k. Now, I don't want to just know what 3t is. I want to know what t is going to be equal to. So what should we do on both sides of this equation to solve for t? I need to divide by 3. So that's going to give me t equals pi over 9 plus 2 pi over 3k. And I'm going to get 5 pi over 9 plus 2 pi over 3k. So these are the actual solutions for t. Okay, now you're pretty much doing the same work. Okay, now why did the period change? Well, notice that that's a b value for the cosine function, right? And to find the period, we usually do 2 pi over b. So that would be 2 pi over 3. So that's just the new period of this function here. Okay, so that's why we're adding 2 pi over 3, because that's a period of function. And again, this would be the angle if it was 0 to 2 pi. But since it's 0 to 2 pi over 3, it's actually the pi over 9 and the 5 pi over 9. Okay, so it just changes. Okay, but again, using the substitution kind of is helpful when we're working with these equations. All right, the next one, similar situation. Now we have x over 2. Okay, so what we need to do is, again, use substitution. This time I'm going to let u equal x over 2. So I get 3 tangent of u plus 3 equals 0. 3 tangent u equals negative 3. Tangent u equals negative 1. All right, so I'm looking for where the tangent is going to be equal to negative 1. Okay. Don't forget that tangent is on the interval from 0 to pi, so there's only one location where tangent's equal to u, and that is going to be where u is equal to 3 pi over 4. Okay, that's going to be the only solution where tangent is equal to negative 1. But we're not solving for u, right? So again, there's no restrictions. So this is going to be u is equal to 3 pi over 4 plus pi k, because the period of tangent is pi. We substitute x over 2 into the equation. Okay, and then we're going to multiply everything by 2. So we're going to get 3 pi over 2 plus 2 pi k. So there's your solution. Okay, 2 pi is now the period, right? Because to find the period for tangent, it's pi over b. So that's going to be pi over the 1/2, which gives me 2 pi. All right, so there you go. There's how you solve this one. Again, when it's multiple angles, there's nothing different. We're just applying this new u substitution property, and then just don't forget to resubstitute u into the equation once you have your answer. All right, okay, the last one for the day, okay, I know this has been a long video, all right, is this one here. So we need to go ahead and solve this. So again, an identity popped up here. So we're going to substitute 1 plus tangent squared in that position. Minus 2 tangent x equals 4. So I get tangent squared x minus 2 tangent x. And if I move everything to one side here, I'm going to get a minus 3. Let's factor that. I get tangent x minus 3 times tangent x plus 1. Okay, when we're going to set these equal to 0, we're going to get a solution here. So we're going to get tangent of x is equal to 3, and tangent of x is equal to -1. Okay, so we are looking for these two function values. Okay, so the first thing is that tangent doesn't really have an angle that is equal to 3. Okay, that's not really a nice one to work with, but we can actually go ahead and just apply the inverse properties, right? So what's the inverse of tangent? Is arctangent. So arctangent of tangent of x is equal to the arctangent of 3. So x here is just going to be equal to the arctangent of 3. Now the reason that's why that's allowed is because don't forget that the range of tangent is from, this is the range of tangent, -infinity to +infinity. Since the range of that is possible, then I know that this is going to have a solution. We just don't know what that solution is going to be. So whatever the arctangent of 3 is, which is most likely a decimal, is going to be the solution for this one. The second one is more traditional. So the tangent of x is equal to -1. That's going to happen at x equals 3 pi over 4. Okay, and then again, it's 3 pi over 4 plus the period, so that's going to be pi k. All right, and then the same thing here, which I forgot to include. You're going to add the period. Plus pi k. All right, and there you go. There's your two solutions. So one was more traditional, the other one's not, but don't forget that tangent actually can equal every single value on the number line because its range is infinite. Same thing with cotangent. So just be aware that those actually have, specific values, whatever. All right, so hopefully this video helped you out. Hopefully you guys tried a bunch on your own. There's many different ways of solving these things. But again, what's important is once you solve them, identifying where they lie in a unit circle. If there's no restriction to the domain, make sure we add the period to the function to get every other value in the domain as well. But yeah, that's it. That's pretty much it. That's some basic trigonometric equations, okay? All right, hope this works out. Hope you guys are enjoying your time, and look forward to seeing you guys eventually, hopefully. All right, so see you soon. Later.